separate content or something like that.
I think we're... Hang on.
Should be shortly.
Yeah, we're on. Yeah. So good to go? Yeah. Right, welcome to the physics only content. I'll try and be quick, I know we're running slightly over. Okay, back to Spec 5. So the first thing that we want to look at in Spec 5 is something called moments. Now the moment is basically a turning force. So a turning force happens when we have a pivot. And when we have a pivot and a force is applied at the end of a lever, we get a moment. Now, here is an example of that. We've got a pivot taking place here. We've got a load, which in this case is a nail, and we've got a force being applied. Now this is effectively a way to increase the force that is acting on something. So if you've ever tried to open a door by pushing really close to the hinge, it's really difficult. So we actually, when we open doors, we use handles that are right on the outer edge. And the reason for that is because we are multiplying the force by increasing the distance. There is an equation that we need to know. The equation is moment, the turning force, is equal to the force in meters, the force in newtons times by the distance in meters. Now, I said earlier, we don't measure work in newton meters, and that's because we measure moments in newton meters, where it is force in newtons times distance in meters. Now, if we want to increase the force acting in this situation here, one way to do it would be to lengthen the distance from the pivot, and that would basically increase the turning force. This applies in all sorts of situations. You might have a seesaw where when you have a small child playing on a seesaw, in order to go on a seesaw with a small child, an older child might have to sit closer to the pivot, and that would mean that the forces were equal, or the moments were equal. The second thing in Spec 5 that's physics only is pressure. Now there are two pressure equations. The first one you need to know, and it's pressure is equal to force divided by area. Again, force in newtons and area in meters. So the acceptable, meter squared. So the acceptable units for pressure are newtons per meter squared, or we can also measure these in pascals, another physics quantity which is named after a crazy French guy. You can see in this situation here, we've got the same object which has a force or a weight of 100 newtons, and by laying it on one side we have a pressure of 1000 pascals, and by laying it on a different edge with a smaller area we have a much larger force. Okay? You need to remember this. The other pressure equation is here. This one is to do with the pressure above you in a column of water, and because it's the pressure above you, it depends on a couple of things, or a column of fluid. It depends on the height of the column above you. So the pressure in fluid increases when there is more fluid above you. It increases when the density of the fluid increases. So if you were to swim in golden syrup, for example, the pressure acting on you will be significantly higher because the density of golden syrup is much, much higher than the density of water. If you were to swim in a vat of vodka, then the pressure on you would be much less because the density of alcohol compared to water is much less. So density has a major effect on this. And the final one is gravity, because gravity is basically provides the weight of everything pulling down on you. So without gravity, there would be no pressure because it's gravity that effectively pulls down on you. If you see the words in your exam, use the physics equation sheet, then what that means is that you are going to be using this equation here, because this equation is on the equation sheet. If you don't see the words use the physics equation sheet, then what that means is that you need to use this equation, and this equation comes from your memory, so make sure you know that equation. Just to show you what that might look like, we have a diver. As the diver positions change, the pressure she is under changes too. So if this diver goes deeper into that column, the height of the column above her increases. And because the height of the column above her increases, the pressure she is under also increases. Okay? The density of the liquid doesn't change much, but the pressure will definitely change. You can see that in this diagram here. What we can see is this container has 3 holes in it, and these 3 holes, the distance that the water is coming out of these 3 holes is dependent on the depth down the can. And it's because above this point here, above hole 1, we have a height of that much above the hole. In hole 2, we have a height of that much, and hole 3, we have a height of that much. You can see that every time the height of the column above decreases, then the distance that the water gets pushed out of the hole by the pressure also decreases. What we'd also see, as the water level dropped, then the water would not travel as far out of the hole because the height above would drop, and therefore the pressure would drop. So these holes would gradually recede towards the can. Okay. Right, so that's the Spec 5 stuff. I've tried to rattle through that as quickly as possible. There is some stuff that you might want to look at on momentum. The momentum equation, I'll quickly jot down for you, is momentum is equal to mass times velocity. And we also need to think about the force, the change in momentum equation. That one is on the equation sheet. It's one of the reasons why I haven't gone through it tonight, which is force is equal to change in momentum divided by time. And basically the whole premise of that equation is that if you increase the time that something's momentum is changed over, then the forces involved in the change will decrease. And this is linked to things like car safety. Nice long crashes lead to low forces. That's why if a car looks completely mangled after a crash, the chances are that the people can get out of that crash and walk away safely because the forces acting on them have been massively decreased. All right, as I said, back onto waves. So with waves, there are 3 things that we need to be aware of and 3 words that we need to effectively use in the physics-only content. And they are transmission, absorption, and reflection. And these 3 things don't happen independently. These 3 things all happen at the same time. So if we have a glass window here, and we have some light which is incident on this glass window, a little bit that light will refract slightly when it goes through. Most of that light will be transmitted through that glass. At the end of the day, that's the reason why we choose glass to make our windows out of, because the light passes through it. The second thing that will happen is some of that light will be reflected. And if you were listening to Mr. McDade earlier, you'll remember that that follows the law of reflection, where the angle of incidence is equal to the angle of reflection. Not so much of the light will be reflected, maybe 15%. The rest of it will be absorbed. And what will happen is, because that light's absorbed, that glass will actually get slightly hotter. So at the end of a sunny day, the glass window will be hotter than it was at the beginning of the day, but most of the light is transmitted and a little bit of the light is reflected. It's important that some of the light is reflected, otherwise, if it wasn't, then we'd walk straight into the glass. We wouldn't be able to see it at all. So all 3 of these situations are going on all the time, and it's up to us to decide and to basically interpret when those things are happening. Second thing I want to just look at, we've already looked at this diagram, this comes in with a required prac. So because it's on a required practical, I wanted to just bring it into here. The required practical is called the light required the practical, and it boils down to 2 things. Part of it is refraction, and part of it is reflection. So the reflection bit was done last year. So because the reflection bit was done last year, it is quite likely that if it's to come up this year, it will focus on refraction. Now I think it's all going to be coming down to measurements, ways to improve measurements. Because at the end of the day, if this angle of incidence is supposed to be 35, and your angle of reflection that you measure is 32, then that is an error. Don't forget, errors boil down to 3 types. We've got random error, probably to do with people, systematic error, or a particular type of systematic error, which is a zero error, where zero is in the wrong place. So when we're looking at improvements, one of the major ways in this experiment would be to look at something like a digital protractor. And a digital protractor, yeah, I didn't know they made such a thing either, can measure degrees to basically to 2 decimal places, and they reduce random errors. So they make it so that when we're measuring these angles, we can have a really, really precise measurement. That's really important when we come look at some of the more complicated aspects of waves. When we're talking about different colours and different refractive indexes that aren't very different at all, we need really, really precise measurements. We need to make sure that these angles that we're measuring are as accurate as possible. We've also got repeating experiments. Repeating is important, less important in physics, because with physics it either works or it doesn't work usually, so repeating is not that much, and if we do have the presence of anomalies, often they're due to random errors or experimental flaws. Right, sound waves come into the physics only stuff, and one of the ways that we use sound waves in physics is for detection and for exploration. So what we can see here, this is a sunken treasure ship. Now this sunken treasure ship was located using sonar, and when the ship was located, it was done so by a boat on the surface, and that boat on the surface, there it is, sent down sonar waves from the machine on the boat. These sonar waves reflected, and they reflected in different amounts of time depending on whether they hit the bottom of the ocean or the boat. These times and the knowledge of the speed of sound in water led to a calculation of depth, and therefore a 3D image of what's going on there. Now there's a really important part of this equation that you need to know, because without this bit, it's just basically speed equals distance over time. And it's this half here, because what we're doing is we're measuring sound going down to the boat and sound coming back up from the boat. So the depth is actually half the speed times the time. So we need to make sure we put that half in. This could also be a case if we're making, if we're doing the speed of sound in air, and we are doing an echo against a wall. Really similar question to the one that I'm trying to describe here was on the trilogy paper last year. The sound coming back and bouncing off a wall means that we need to add in that half just to make sure it's right. The equation here, just to show you an example, a sound wave which travels at 1,350 meters per second, takes 0.4 seconds. We just plug those numbers in just like that, which would give us the depth of the sea. Making sure that all the readings are accurate, that would give us a depth in meters. The other part of sound waves for detection and exploration is to do with the Earth. Now, when an earthquake happens, 2 types of waves are produced. Earthquake epicenter there, and we get a P wave and an S wave. P wave literally means primary wave. And just like primary school, primary waves are the first waves. This is because they are faster. They move quicker than secondary waves. Secondary waves are therefore slower. The faster wave will move to the surface of the Earth much, much, much quicker, and will be felt and will be the first effects of the earthquake. These actually aren't that dangerous and aren't that damaging, because if you imagine if you're stood on the Earth here and a wave comes up underneath you, a longitudinal wave, then that would move you up and down slightly, but moving up and down slightly won't make you fall over necessarily. It'll just give you a bit of a shock. So they're not actually that dangerous. With earthquakes, it's the secondary wave that causes all the damage. And the reason for that is because these are transverse waves. And these transverse waves will actually move our chap from side to side. Moving you from side to side leads to much higher chance of you falling over, much higher chance of the building that you're in falling over. So these are much, much, much more dangerous. Okay, the second thing about this that's really, really important is this. It's probably quite hard to tell here, but there we can see that we have P and S waves seen. But there we only have P waves. So the best way I can describe this is that Earth acts a little bit like a giant bell. And when an earthquake happens, it's like that bell being struck. And when the bell is struck, the vibrations pass all throughout the Earth. So they start spreading out in all directions. In this area, we get P and S waves. However, over here, we only get P waves. And that means that there's something stopping the S waves. Now, it's long been known that transverse waves don't travel well through liquids. So the inference of this situation is that there is something liquid in the way that's stopping the S waves from getting to the other side of the Earth. And that's where the theory of a core made of liquid in the centre of the Earth comes from. Well, that's one of the theories. There's also a shadow zone, and that shadow zone is a result of refraction. So that adds a little bit of evidence to that situation. Also in waves, we've got lenses, and lenses produce images. So a couple of things that we need to know about images. We need to know, basically, are they real or not? Real means that the light converge, the rays of light converge on each other. So you should be able to see in this diagram, these two rays of light meet at a point, so we have a real image. When we're talking about images, we need to know whether or not they're real. We need to know their size. Are they magnified? Are they the same size? Or are they diminished? And diminished means that they get smaller. Finally, we need to know whether or not these images are erect, which means that they are the same way up, or whether or not they are inverted. In this situation, this image is inverted, and it's magnified, and it's real. This is a convex lens, just incidentally. Didn't mention that very well before. Convex lens go out, and this is a concave lens, and concave lenses go in. Just to draw your attention here, these lines here, these are dotted lines. That means they don't really exist. So when we construct the ray diagram for here, what we find is that light is diverging. And because its light is diverging, what we do is we track these light rays backwards until they meet. But they're not actually meeting, so it's what's called a virtual image. It's not actually there. So they're not actually converging, they just appear to. If we look at this image here, this is significantly bigger than this one, so we would describe it as magnified. And as I said before, it's the right way up, so that means we have to describe this as erect. It's not the ideal word to be using on a live YouTube stream, but unfortunately I don't make up the terminology. So, just to show you how to construct these, because I think drawing lens diagrams is really easy, but it's only really easy if you've done it recently. So the first thing is we draw a line. All our lines start at the top of the object, and the first line goes directly, using a ruler, through the centre of the lens. And we just keep on going as far as we need to. The second line goes from the top of the object, parallel to the principal focus until it hits the lens, and then parallel to the principal axis, and then it goes through the principal focus. The principal focus will probably be labelled F. Now you go through there, follow that line in a straight line until the lines cross. This third line is not necessary, but it is a good checking mechanism, so it's worth doing it. Because if you follow that one, again through F this time and this time, and then along there, the line should converge at the same point. That's the top of your image. So it's the same as this, and it's there. And what we can see is, what we've probably got is something that is inverted, probably the same size, and it's real because these are real light. Don't forget, in ray diagrams, a convex lens will be represented like this, and a concave will be represented with the two arrows going in. So just to show you what that looks like for a concave lens, just very quickly draw a quick concave lens diagram. There is our object. The first line, as I said, goes straight through the principal axis. There is F. The second one goes parallel to the principal axis and then through the principal focus. Notice that these lines are starting to diverge. So because of that, we trace backwards, we do dotted lines. Obviously all of this will be done with a ruler, and then we end up with the lines converging at that point, and then that gives us our opportunity to describe it with our three words, talking about size, talking about whether it's the right way up, and talking about whether it's real or whether it's virtual. You also in waves need to know specifically about visible light, that section between infrared and between ultraviolet. Luckily, infrared and ultraviolet bookend the visible light spectrum really nicely, and the visible light shows the exact same pattern that we would see in infrared. The longest wavelength at this end, the shortest wavelength at that end, so wavelength going from right to left, the highest frequency in the blue coloured light, and the highest energy. Now this is important because depending on the frequency, depending on the wavelength, light interacts with matter in slightly different ways. And you can see here that what we have is the refractive indexes of 4 different colours. Now these numbers are not vastly different, but they are different enough to give us some interesting things. What you'll see here is a rainbow of light. That rainbow of light happens because the different colours of light refract by different amounts when they pass through a block. The violet light, which has a higher refractive index, bends more than the red light. So when we bend the white light twice in the same direction as we do when it goes through a prism, we end up with violet light bending more and red light bending less. So we actually split the spectrum into a rainbow, and that's why we get a rainbow colour. Light's really important as well when we come to think about why we see things in certain colours. So the different frequencies of light depend on, the colours of light are determined by the frequencies. So the easiest place to start is white light. Now white light is a mixture of all the different colours, but we're going to go with blue, green and red just to make this easier. White light falling on a white object, all of the light is reflected. So because all of the light is reflected, the object appears to be white. If white light falls on a black object, then all the light is absorbed. So the different frequencies, every single one is absorbed. That's part of the reason that links into infrared and why black objects warm up faster and quicker than white objects. The other three are a kind of combination. So the blue light reflects in this situation, and the rest of them get absorbed. So red and green both get absorbed, blue reflects. In this one, green reflects, blue and red absorbed. And in this one, red reflects, green and blue absorbed. So there's a link here with photosynthesis. So you've probably studied why green plants look green, and the basics is, and what colour light they photosynthesize best in. And the basics are that the blue and the red are absorbed better. There's some filters down here. These are exactly the same, apart from the only difference is, rather than the word reflected, we're going to use the word transmitted instead. Okay. All right. Really quickly, blackbody radiation. Just to be clear, this cup of tea will cool down faster than this one because the energy will move quicker from the area where there's more in it, where there's a bigger difference in temperature. This links into something called blackbody radiation. Now, this is a theoretical thing in physics. It's an idea that something would absorb all the radiation that hits it or emit all the radiation that it has. It's not a real concept. So a black t-shirt would just basically absorb everything, but it doesn't actually happen. It would probably be associated with a graph like this, and there's two patterns that we need to see here. One is temperature, so the higher the temperature, the more energy is released, but also there's a slight shift on this graph. It is shifting slightly to the left, so we've also got a higher the temperature, the shorter the wavelength. Watch out for this. Right, moving quickly on, electromagnetism. A couple of things with electromagnetism we need to know. The generator effect. This is basically motors, but in reverse. So in a motor, we use electricity. And we use electric current to make movement. In a generator, we use movement to make current, or to make potential difference. Because what we have here is a wire inside a magnetic field. Moving that wire causes the electrons within that wire to be pushed around, and therefore, as you can see on the ammeter, we have a current. There are two different ways of making electricity, or generating electricity. There is a dynamo and an alternator. A dynamo makes direct current, D for dynamo, D for direct, and an alternator makes alternating current supply, surprisingly. This is literally a motor. The difference here is that rather than putting current into it and getting it to spin, this time we put movement in and we get current out. It has a slip ring commutator, just like in a motor, and what we have is the movement of the wire around, which causes current to flow. When the coil of wire spins 1/2 turn, the wires swap which side of this slip ring commutator it is touching, and therefore the left-hand side of the wire, the left-hand wire, whichever left wire is on the left, is always moving the same direction through the field. So we get direct current, it's always going the same way. In the alternating current, what we have is two different rings. The red one's always in contact with this one, and the blue one's always in contact with this one. So we have an alternating current. And this alternating current, this moves up and down depending on the position. If we want to increase the current that's made, we need more coils, just like in a motor and electromagnet. We need faster movement, and we need a stronger magnetic field, just like in a motor. You might be asked about a couple of devices that use electromagnets, so I'm going to throw these in quickly. An electromagnet here, this is a, basically it's called a, I can't even remember, circuit breaker. Circuit breaker, when too much current travels through this wire, this electromagnet gets stronger. It pulls that switch open. This is the sort of thing you have in your house at home that's designed to protect you. You have them in circuit break, they call them fuses in the fuse box, but they're not actually fuses, they're circuit breakers. There's another example here. This is called a relay, and this is like your switch to turn your car on. Your car's a big, heavy piece of machinery, quite dangerous. So we use an armature to use a relay basically to turn our cars on. We put a small amount of current in, turning an electromagnet on. The electromagnet pulls an iron armature towards it. That armature is on a pivot, so another part of it moves as well, which causes a bigger switch to be switched on. I'm going to skip past that and go briefly on to transformers. Do need to go through transformers because transformers is really quite tricky. What we've basically got is two different coils. This is called the primary coil and this is called the secondary coil. This one is effectively an electromagnet. And the strength of the electromagnet determines how much energy is generated or how much electricity is generated by this, which is effectively an alternator. Making the electromagnet stronger is done by increasing the current and increasing the number of coils. And changing the amount of current that's generated is dependent on the coils and the strength of the magnetic field. So basically, what we have is a really strong link here between the voltage that we put into this one and the voltage that comes out of the second one. We call this the primary, as I said, and that the secondary. That is really strongly linked to the number of turns on the first coil and the number of turns on the secondary. That equation's on your equation sheet, but it's a lot more straightforward than people think it is, because what we've basically got here is two fractions that are effectively the same as each other. So if our voltage on the primary is 2000 and our voltage on the secondary we want to be 40, we need to make sure that the ratio of 2000 to 40 is the same as the ratio of the number of turns. So if I have 4,000 turns on the first one, we need the number here that makes these fractions equivalent to each other. So therefore that is 80. That's what I just said there. Another thing we need to know about this is that we've got power. We assume that these are 100% efficient. So what we say is that the power on the primary is equal to the power on the secondary. That's what this says here. V times I on this one is equal to V times I on that one. And again, it's a lot more straightforward than people think it is. Let's say that the current on the first one is 20 and the voltage is 12, and on the second one the current is 40. What we're looking for is another number pair that give the same answer as that, so that one would therefore be 6. Finally, spec 8. This is the only one that is physics only. It's a really short spec, but because it's physics only, it's absolutely certain that it's going to be assessed. The first thing I want to look at is life cycle of a star. Now, life cycle of a star is wholly dependent on gravity. Gravity causes a nebula to start to collapse in on itself. As the nebula starts to collapse in on itself, it starts to get hot. We call it a protostar. Now, not all stars make it. Some stars don't make it, and the stars that don't make it we call brown dwarf stars. They didn't make it because they weren't big enough. And that's basically the same pattern that we see all the way through the star's life cycle. Stars that do make it are called main sequence stars. Our sun is a main sequence star. Small main sequence stars stay like that for a long time until eventually they become red giants. When they become red giants, they basically run out of hydrogen, they start to fuse helium, and eventually the gravity can't hold them in place anymore. Part of them comes off to make a white dwarf, the rest of them drifts off into space to become another nebula. Big main sequence stars will become super red giants. The only difference between a red giant and a super red giant is size. These are proper big. So because they're really big, when gravity can no longer hold them in place, the outer layers don't just drift off, they explode. They supernova. When they supernova, the outer layers go off and become a nebula, but we have two possible situations. We have a neutron star. Neutron stars are like white dwarfs, but they are denser. And because they are denser, no light escapes at all, only X-rays. Black holes are even denser, and those black holes are so dense that not even X-rays can escape. So basically, neutron stars are nearly black holes, but they didn't quite make the cut. As I said, it's all about gravity and size. The bigger, the more likely it is to go along this route. Smaller, if they make it at all, will just become main sequence and red giants. This is what I was saying before. Most of the life of a star, we have gravity pulling in, and at the same time, the radiative pressure from the star pushes out. Certain points in a star's life cycle that changes. So for example, when it becomes a red giant, the radiative pressure pushes out greater. It wins until the forces equal each other out again. And then when it supernovas or when it comes to the end of its life as a red giant, the radiative pressures win again and the outer layers drift off. Really close to the end now. A couple of things in terms of orbital speed. I'll just drop this in really quickly. When two objects are closer to each other, the forces between them are stronger. Because the forces between them are stronger, in order to keep something in orbit, the velocity has to be higher. So the closer an object is to the object it's orbiting, the faster it needs to be. Therefore, Mercury is the fastest planet in the solar system because it's the one that's closest to the sun. The slowest planet in the solar system would be Venus, Jupiter, Saturn, Uranus, Neptune would be the slowest because it's the furthest from the sun. Pluto's not a planet before I get any comments. Skip that one, covered it earlier. And finally, redshift. So really, really important part of physics, this, redshift. When an ambulance moves towards you, the sound that it makes gets squashed up. It appears to sound higher pitched than it actually is. This is called the Doppler effect. You've all experienced the Doppler effect. If you've ever played with like a Nerf rocket or anything like that, you've heard the Doppler effect. That's with sound, but the Doppler effect also happens with light. So Edwin Hubble was his name. He basically, really famous physicist. He looked at a load of galaxies, he looked at a load of stars, and he looked at the light coming from them, and he noticed that the light coming from them was redder than it should be. If you look at these black bars in this picture here, this is the laboratory standard. This is light coming from you know, a control study in a lab. The light coming from the distant galaxies, all of these black lines were shifted that way. This light was red shifted. Basically, what was happening here is that the light was being spread out. It was like being behind the car in the Doppler effect. What we noticed then was that basically every galaxy that we looked at in the night sky was red. And the redder it was, the further it was from us. So Edwin Hubble was a really good scientist, so he plotted a graph, which is what you should always do when you've got some information. And he noticed that the recession velocity, the speed of the galaxy, and the distance of the galaxy were linked in a nice positive correlation going up in that direction. Basically what that means is the further a galaxy is from us, the faster it's moving. So he did some logic, and he said this, and this is the last one. All the galaxies, there is one exception, but I won't go into it right now, are moving away from us. The furthest galaxies are moving the fastest. And the reason for this is because they have been moving for the longest time. And then this is where he made his major leap. He said, how about if we rewind the tape? If we look back in time, they must have all been closer together. So if you keep rewinding and keep rewinding and keep rewinding, you get to a point where everything was in one point. And if everything was once in one point, it must have started expanding at some point. Ergo, Big Bang. You might get asked to use Redshift to explain the Big Bang theory. Okay? Just remember the Doppler effect and remember spreading out waves. Thank you very much for tuning in tonight. Thank you very much for your attention. We're really sorry about the technical difficulties we had in the middle. Hopefully it's been of some use to you, and feel free to re-watch.
Thank you, Year 11. Good luck for tomorrow morning. Remember, Horizon students, remember where your boosters are. So make sure you get here bright and early. We start at 8 o'clock. If you're here at 8:10, you'll not be allowed in. Thank you very much. Good night.